Taking a look at this series, we're going to again do our ratio test to find the radius. We can see that there's no horizontal shift, so I'm going to establish my center is going to be at 0. Okay, and then I'm going to do my ratio test for the radius of convergence. Once I get the radius, I know what x values represent my endpoints, and then I need to make sure I test those endpoints. First thing though is we're going to set up our ratio test. We always start with our ratio test. So we're going to have in the numerator, we have -1 n plus 2. We have x to the power 2n plus 2. When I substitute in n plus 1, I get 2 times n plus 1. So I get 2n plus 2. And in the denominator, I'm going to end up with 2n plus 2. The denominator of that was the denominator of the numerator expression. So in the bottom, I'm going to have -1 to the n plus 1, x to the 2n, and over 2n. And this ratio test has to be less than 1. So rearranging this, we end up with limit n to the power infinity. I'm going to group my ones terms, -1, so I get -1 to the n plus 2 divided by -n to the n plus 1. That just leaves me with one -1 factor. Group together my x terms. My x terms will have x to the power, should we do that? It's going to be x to the power of 2n, and then x squared. In the denominator, I'm going to have x to the power 2n. That'll be grouped together because things will cancel out there. For the n terms, I end up with 2n plus 2, and in the numerator, it's 2n, and I'll group together those terms as well. The limit of those red brackets, 2n over 2n plus 2, as n goes to infinity, that's going to be equal to 1. The -1's not going to be relevant when we have the absolute value in here. So what we can do then is we can cancel out these factors, and what I'm going to end up with is x squared times 1. Okay, so maybe I'll do the x squared in green. That comes from the green bracket, so x squared is going to be less than 1. Okay, so what that means is that x squared is going to be less than 1. Well, x squared is going to be between 0 and 1, but x could be between -1 and +1. So that's going to then establish my interval. I have a radius of 1. Okay, so the x squared, if it was anything from -1 to 1, it would satisfy that inequality. So at this point, I have my radius. The radius is now 1. And we can then test our endpoints to see if the endpoints converge. So I'm going to test my right-hand endpoint first. Okay, so I'm going to test x equals 1. Plugging x equals 1 into that expression, x or n goes from 1 to infinity, -1 to the power n plus 1, and this will be 1 to the power 2n. That won't affect anything over 2n. So simplifying this is our harmonic series divided by 2, and it is alternating because of that -1. So this is an alternating harmonic series. Therefore convergent. Okay, so we're going to include that as one of the endpoints. So at this point, if we were to draw our number line in, we have our center is going to be at 0. We have a radius of 1 to the right. This endpoint is going to be convergent. And then we're going to go 1 to the left and test that. And that's going to be at -1. So we'll test that endpoint. And we'll test to see if that is convergent or divergent. So testing the -1. So x equals -1. This is our test. And this is just any test we can use. It could be just a direct comparison. It could be just from a known series. We end up with -1 to the power n plus 1. When we substitute a -1 this time, we're going to end with -1 to the power 2n over 2n. Now, this power is always even because of the 2n, and that means that that -1 is just going to end up being 1. So we can then say that this series will be an alternating harmonic series, okay, based on our simplification. Again, it's an alternating harmonic series, therefore convergent as well. So we'll fill in that endpoint. We've included that endpoint. So summarizing this, we have our interval of convergence is going to be from -1, including -1, all the way to +1, including +1. It is a closed interval from -1 to 1. Okay, these are just describing the exact same things. Essentially, we have convergence with a center at 0, radius of 1, and an interval of -1, including -1, all the way to 1, and including 1. Again, we did this by ratio test first. That's always our first test that establishes the radius of convergence. And then we test the endpoints using some other method. If we need to, we can go back to the ratio test, but we are testing this, or we are determining convergence or divergence in any way, whether it be a formal test or an informal test or a comparison like we did here.